Today we're covering projectile motion, very important for all of our athletes out there who play games that relate to getting a projectile in a goal, in a basket, into somebody's hands. So let's get on with it. So the definition here that you read about in your book is that a projectile is anything that is projected or launched to begin with. Maybe it has a launch angle that is from 0 to, it could be from 0 to 90, although 90 degrees from horizontal makes it something that would go straight up and come back down, which we already covered. That was free fall. So if it's launched at 0 degrees, basically horizontally, then that has to be like a situation where it's going to be launched off of some kind of cliff or table or something, and then it's only going to go down. If it's launched from the ground, then it'll go up and come down in the parabolic trajectory that we would be used to. Even if you think about it, like in this last picture, this woman is just throwing a basketball straight up and down, but she herself is moving sideways. And so if you are an observer that's watching that from, if you're standing there watching her, you would see this as projectile motion of the basketball, because the basketball has forward motion from the fact that she has forward motion. So that counts too. It's in that case, like, it's a matter of your perspective, because from your perspective as the person standing there, it was projected forward. From her perspective, it's a free fall problem, because as she looks up at the basketball, it's just going straight up and down. So that's kind of interesting. But here, it's also important to remember that we are again simplifying these problems and imagining that once they are launched, it is up to gravity. So we are ignoring air resistance again. We are not worrying about the action of launching the thing. We are just worrying about how it's moving after it's been launched. And then as we try to solve math problems and predict the motion of something that is moving in this way, okay, the important things we have to remember is that this is only under the influence of gravity. So we would say that it is not accelerating in the forward direction. It is only being affected by gravity, which is pulling it, accelerating it downward. So that really sets us up for some equations. Now, these ones I took from another textbook, but they should match up with our AP equations. And we are plugging in, if you look on the left-hand side, here are the x direction equations. But what we're doing here is we're just remembering that what I just said, that in the x direction, there is no acceleration. And then what is the initial velocity? Well, what initial velocity was it launched with? If it was launched at an angle, well, even if it was launched at 0, right, the cosine of 0 degrees will be 1. And then you'll have 1 times that initial launch velocity. Okay, and then you get to plug that in. And notice that the last term, like the plus 1/2 AT squared stuff that's on the AP sheet, has disappeared because that acceleration is 0. And then you can also have the third equation that would help you solve for, well, but we don't have acceleration, so what am I talking about? This is the only way to solve for the x, or the position in x, okay? And then for the y direction, we take that totally separately. It's totally independent. And we use negative 9.8 as our acceleration, assuming up is positive. Okay, and we use all the same equations we did for free fall. And we just remember, though, that we have to take the y component of the launch velocity, because that's the only part of the velocity that gravity is going to have an effect on. So gravity doesn't have any effect on the part of the velocity that that is the forward part. It only has the power to slow down and then eventually speed up on the way back down the velocity in the up-down direction. Okay, so this is difficult to remember, but x and y for the projectile are totally separate, and the only thing that links them together really is time. And then, of course, we have, if we're splitting the initial velocity into its components, then we have that in the angle we were given. The book mentions the word trajectory, so that's important. That might come up. And that parabolic path through space. It mentions the range, which is used to refer to like how far along the ground, or how far in the x direction has this projectile moved. And it happens that you can prove this mathematically, but you will get the maximum range if you launch a projectile at 45 degrees. I do not like using, I know they give you formulas for, like solving for y without time, solving for range without the time variable in there. But we found last year that trying to use those formulas, it might cause trouble because they're using certain assumptions that might not be valid for every problem. Okay, so we will be doing some math problems, and I'm going to do those in separate videos, so I'll leave it here for now.